Have you ever wondered where stars come from? It's a question as old as humanity itself. Yet the answer lies not in the twinkling points of light we see in the night sky, but in the darkness between them. This is where the vast cosmic ocean of gas and dust, known as the interstellar medium, cradles the birth of stars. Within this seemingly lifeless void, a complex and fascinating process unfolds, leading to the creation of a protostar. The birth of a protostar is a celestial event of cosmic proportions. The birthplace of stars, known as giant molecular clouds, is a sight to behold. These clouds are no ordinary clouds, but rather an extensive expanse of gas and dust. This area, my friends, is the interstellar medium, a vast and diverse environment that serves as a playground for the birth and death of celestial bodies. The interstellar medium is not merely an empty space, but it is teeming with a staggering amount of hydrogen, helium, and a smattering of heavier elements. These elements are the building blocks of stars, and their abundance in the interstellar medium makes it the perfect stellar nursery. Now, within this stellar nursery, you'll find an impressive sight, the giant molecular clouds, or GMCs for short. These are not your everyday cumulus clouds. They're colossal structures that stretch across hundreds of light years, containing millions or even billions of times the mass of our sun. The significance of these GMCs cannot be overstated. They are the cradle of stars, the place where all stars, including our sun, first find their spark. But how does a star begin its life in such a cloud? It all comes down to a few key triggers that cause dense regions within these GMCs to collapse. The culprits could be shockwaves from supernovas, the powerful outflows from young stars, or even gravitational interactions. It's like a cosmic domino effect, where one event sets off a chain reaction leading to the birth of a star. When these dense regions start to collapse under their own gravity, they create a concentrated area of gas and dust. This is the beginning of a new star's life, the first step on its journey from a simple cloud of gas to a blazing beacon in the night sky. The collapse of these dense regions is not a quiet affair, but a dramatic transformation filled with cosmic energy and raw power. These dense collapsing regions set the stage for the birth of a protostar. It's here, in the heart of these collapsing clouds, that a star begins its life. And so, the cycle of stellar life continues, with each new generation of stars born from the remnants of their predecessors. As a dense region collapses, a celestial wonder is born, a protostar. In the heart of the vast ocean of gas and dust known as the interstellar medium, a transformation is taking place. A region within a giant molecular cloud, already dense with matter, begins to collapse under its own gravity. This collapse is not a gentle process. It's a violent and turbulent event, driven by shockwaves from supernovas, outflows from young stars, or gravitational interactions. As matter is drawn inwards, a dense core forms. This is the birthplace of a protostar, but it's not alone. Surrounding the protostar is a swirling disk of gas and dust, known as the protoplanetary disk. This disk is more than just a cosmic accessory. It plays a pivotal role in the creation of planets, asteroids, and other celestial bodies. Over time, the material in this disk begins to coalesce, forming larger and larger bodies, until eventually, planets are born. But let's not get ahead of ourselves. Back at the center of this cosmic maelstrom, our protostar is undergoing dramatic changes. It's growing hotter and denser as more and more matter falls into it. Eventually, the protostar becomes so hot and dense that it begins to undergo deuterium burning. This is the protostar's first step towards becoming a true star. Deuterium burning is a kind of nuclear fusion, but it's not the kind that powers stars. Deuterium is a form of hydrogen, and it's much easier to fuse than regular hydrogen. This process generates a lot of heat, and it's this heat that prevents the protostar from collapsing further. As the protostar continues to evolve, it grows hotter and denser, and then something extraordinary happens. The core of the protostar becomes so hot and so dense that hydrogen atoms begin to fuse together to form helium. This is hydrogen burning, the process that powers stars. The protostar is now a pre-main sequence star, a star in its infancy. The protostar, having ignited hydrogen fusion, is now on its way to becoming a main sequence star. The journey is far from over, but the most significant steps have been taken. The protostar has emerged from its birthplace within the dense molecular cloud. It has formed a protoplanetary disk, it has undergone deuterium burning, and it has ignited hydrogen fusion. The celestial wonder that began as a dense region of gas and dust is now well on its way to becoming a true star, a beacon of light in the vast expanse of the cosmos. Observing these newborn celestial bodies is no easy feat. You see, protostars are like shy infants hiding behind a veil of interstellar dust and gas. This cosmic veil obscures the visible light, making it quite a task to catch a glimpse of these stellar babies. But as with many things in life and space, where there's a will, there's a way. Astronomers have mastered the art of peeking through this veil by relying on infrared and radio observations. These forms of light have longer wavelengths than visible light, allowing them to pass through the dust that blocks our view. Infrared observations are like the superhero of stargazing, capable of revealing the warm glow of dust grains surrounding the protostar. This glow is the telltale sign of a protostar at work, its heat and light causing these grains to radiate in the infrared part of the spectrum. Thanks to infrared, we're able to observe the birth and early evolution of stars. On the other hand, radio observations provide a different but equally valuable perspective. They let us see the bigger picture, the overall structure of the stellar nursery where protostars are born. We can observe the gas and dust clouds' motion, providing insights into the complex processes at play during star formation. But it's not just about observing, it's about understanding. Each observation is a piece of a cosmic puzzle. Every infrared glow and radio wave adds to our knowledge of these celestial infants' birth and evolution. They help us form a picture of the life of a star, from its humble beginnings in a dense cloud of dust and gas to its fiery entrance onto the main stage of the cosmos. Despite these challenges, each observation brings us one step closer to understanding these cosmic infants. We might not have all the answers yet, but with each protostar we observe, we're getting closer to unraveling the mysteries of the stars. Protostars, much like humans, come in all shapes and sizes. The universe is a diverse place, and this diversity extends to the stellar nurseries where protostars form. These cosmic infants, born from dense regions within giant molecular clouds, come in a variety of types, each with its unique path of evolution. The mass of a protostar plays a significant role in determining its future. Low-mass protostars, for instance, take their time in the cosmic playground. They evolve at a slower pace, undergoing a process known as deuterium burning, before they ignite hydrogen fusion and graduate to become main-sequence stars. On the other hand, high-mass protostars are the overachievers of their stellar nurseries. Their larger mass results in a higher core temperature, allowing them to bypass the deuterium burning phase and jump straight into hydrogen fusion. This rapid pace of development, however, comes with a trade-off. High-mass protostars live fast and die young, exhausting their nuclear fuel quicker than their low-mass counterparts. Despite these differences, both types of protostars share a common starting point, a dense region within a giant molecular cloud. They also share the same ultimate goal, to ignite hydrogen fusion and become a main sequence star, contributing their light to the cosmic tapestry. So, you see, whether big or small, each protostar has its unique journey in the vast cosmic ocean. The birth of a protostar is truly a cosmic spectacle. From the vast interstellar medium, an ocean of gas and dust, emerges the stellar nursery, the giant molecular clouds. These clouds are the cradle of protostars, their dense regions collapsing under various triggers such as shockwaves from supernovas, outflows from young stars, and gravitational interactions. This collapse birthed a protostar, enveloped by a protoplanetary disk, an essential element in the formation of planets. The protostar evolves, undergoing deuterium burning before igniting the fusion of hydrogen and thus becoming a main sequence star. Observing these celestial infants is no easy task, with their light often obscured by dust. However, infrared and radio observations have allowed us to glean valuable insights into their existence. Not all protostars are created equal. with high-mass protostars evolving at a faster pace than their low-mass counterparts. Next time you gaze up at the night sky, remember, each star has its own unique birth story, beginning as a humble protostar.